do today is I should be recording now, I think. Yeah, I am. Okay, first thing I'm going to do is this problem, which is very much like problem 6 on the homework. It's kind of a repeat of the one for, I don't remember what we were doing, talking about freezing a lake or something like that. But this one, we've got more extreme temperatures, minus 40 degrees Celsius above the water, and we'd have let's see, 0 degrees Celsius for the water temperature, so a 40-degree temperature difference. And I'll set this up pretty much like I did the one the other day, and I'll kind of show you that we just imagine on that one, I think we had a minus 10 degrees Celsius temperature above the ice, and this was supposed to be 0 degrees Celsius because that's the temperature of the water just below the ice. But we integrated from 0 to whatever it was, 0 thickness to whatever the final thickness was. But I'll go ahead and set one up. And this time we've got a nice rectangular swimming pool, so that'll be pretty easy. And we'll just imagine that we've got some little thin thickness of ice, but we'll be interested in the limit as that little thin thickness of ice goes to 0. And this is a heat flow problem. And so we'll have H equals dq dt. And as far as the heat flow equation, we'll use the thermal conductivity of ice. We'll multiply by the area of the pool, which I don't think we're even given on here, but it divides out anyway. And then we'll have the TH minus TC. So we'll have that there. And then we're going to imagine that we have some thickness of ice X. And at first, we won't even have this, but the equation that we're going to solve is going to be a little bit different. All right, then I want to figure out how much heat does it take, or do we lose when some thickness of ice melts? And usually we think of the heat of fusion times the mass of whatever it is that we're talking about. That's how much heat would come out of the ice. But in this case, I'm going to have some little tiny increment of mass, and so I'll call that dm. And that little increment of mass is going to come because we've got some, this is not an area as it looks like, but this is going to have, this pool will have some area to it. And so the mass of some little thickness of water that's on there is going to equal that area times the dx. That's how much water is going to be changed into ice, and we're going to be ignoring the fact that ice has a somewhat different density than water. But that'll be the volume of a little bit of water. And then if I multiply that by the density of the water, this would be the mass of it. And so the amount of heat that comes out of that, this would be like a dq, little bit of heat. Well, it's going to end up looking like this. The amount of heat that comes out of that little bit of ice, I'll have the L sub F, the heat of fusion of water, the density of water times the area. Now this gives me the, and the dx. That gives me, this is the mass of the water multiplying by the heat of fusion, and that's how much heat will come out of it. And I'm interested in dq dt. So I take this and stick it on top of that. This is the process that I went through the other day as well. So I'll have L sub F rho A let's see, dx over dt. And that'll equal this. K sub I times the area times the temperature difference divided by the thickness of the ice. And so at first, this is going to be very small, but you'd be looking at this in the limit as x goes to 0 and I don't know, dt goes to 0, but we're going to cross multiply here anyway to get rid of that. And I've got areas both sides, so I can divide those out first thing. And if I then multiply both sides by x dt, that has the effect of cross multiplying, I will end up with heat of fusion, density of water, times x dx on one side, and K sub I times A times, whoops, A's are gone, pH minus TC and dt. So this is an equation where I can integrate both sides of it. I don't know if you ever did anything like this in a calculus class or not. I certainly didn't do a freezing a body of water problem in calculus, but I'm guessing I probably had a dx dt and maybe an x on the other side or something. But anyway, we can do this. So let's integrate both sides. Now, here you're imagining that you start from 0 and going to some x final, but I'm gonna, when we get this solved, I'm going to try it for some different values of x initial, and we'll see what happens when we do that. So I can isolate all the variables on one side. By the way, these are all constants. These are constants. So I can lump all of those things together. L sub f rho divided by K sub I times TH minus TC. And then I'll have x dx, and that'll equal dt. And the question is asking, how long is it going to take to do something? Like on this one, how long will it take to freeze the pool solid? And it's got a depth of 2.50 meters. Well,
Oh,
you don't have to do that necessarily.
yeah, no, I'm really just got back into physics. I'm not kidding. Like,
Pardon?
huh?
Oh, I'm going to mute you, James, because I think you're not talking to me, maybe. All right. Anyway, let's integrate both sides of this thing and see what happens. So integrate this one, and I'm going to go from some x initial to some x final, and then I'll integrate this just to find out how long it'll take for the ice to form going from this initial x to this initial final, and I should be able to just maybe set up some different things here. But let's go ahead and integrate this. The right side is easy to integrate. It's going to be t. The left side is going to be those constants, and I'm just going to call these, I don't know, use some favorite Greek letter for them, beta. All of these things together are beta. So, and when I integrate that, I'll end up with x squared over 2 times, whoops, I've got beta on there, I forgot about, integrated from some x initial to some x final. And so the amount of time it takes is going to be beta, let's see, I'll stick a 1/2 beta there, and it'll be x final squared minus x initial squared. Okay, well, what if x initial is 0? Okay, how long would it take to do it? Well, the time will end up being 1/2 beta. If x initial is 0, that just drops off the map, and I'll have x final squared. So that's how much time it would take to go from 0 to that thickness. how long would it take to go from this X final to some X final that's twice as much? Okay, well, then my X initial, well, let's see, this is getting inconvenient here, and possibly confusing the way I'm doing it, but how long would it take if I went from 0 to 3/4 of that X final? What would the time look like? Well, delta T in that case would equal, I'm going from 0 to 3/4 X final, would be 1/2 beta times 3/4 X final is 3/4 squared is 9/16 X final squared. Okay, but I'm only going to 3/4 X final. How long would it take to go from an X initial of 3/4 X final to an X final of X final? Okay, well, in that case, I'll call this delta T prime. And remember, I'm going from 3/4 X final to all of X final. I would get 1/2 beta times my X final is just going to be X final squared. My X initial is going to be 3/4 X final, but it gets squared, so I'd have 9/16 X final squared. That's X final there. And this delta T was going from 0 to 3/4 X final. This one's going from 3/4 X final to X final. And if I add these times together, I would get, I've got a 1/2 beta out front. These two terms divide out and I'd get just plain 1/2 beta X final squared. So once you have this expression, you can use it for all sorts of different intervals. And so just all that you have to change is what the X initial is and what the X final is. So that's something that'll help you on here. And I guess we may as well figure out how long it would take to freeze the pool solid if it would happen. So I think we just need to have X initial is 0 for us. So we would have the time it'll take will be 1/2 beta times X final squared, where X final is going to be 2.50 meters. And we'll have to figure out beta. Beta is that heat of fusion of ice times the density of water divided by the thermal conductivity of ice times the temperature difference, T hot minus T cold. Actually, in this case, yeah, that's right. T hot is 0 degrees, T cold is -40. So let's go ahead and plug in all the numbers here, which for some reason I don't have written down here. Oh, on the back of this. Heat of fusion of ice, if I remember, is 334,000. Yeah, 3.34 times 10 to the 5th joules per kilogram. And then density of water, 1.00 times 10 to the 3rd kilograms per cubic meter. By the way, the weight of that much water is about 2,200 pounds. So that's a lot of mass in a cubic meter of water. I thought about this one time. I was driving over to Seattle, and just for a change, I took Highway 2. And for a while, Highway 2 drives next to the Skykomish River. And there was a place where there was an aluminum canoe. The Skykomish River can flow with a pretty good rate of flow sometimes, but there was a place where an aluminum canoe was folded in half around a bridge abutment, the concrete post that supports a bridge. And it's not surprising that if you've got water moving at a pretty good clip, every cubic meter of that water weighs 2,200 pounds, and it's not surprising that it could fold an aluminum 2.5. And anyway, that's quite a bit. Okay, now the case of I for ice, geez, where was that? That's on a different table. I don't remember what it is off the top of my head. Shoot. It's not on that table. Don't know where I put it. Oh, well, it's in that last chapter. That's where it is. Thermal conductivity, ice. Okay, 1.6 watts per meter Kelvin. So and then multiply by 40.0. And this is the temperature difference. Kelvin and Celsius are the same for those things. So we can just get a number for that and see what it's going to be. Okay, beta is going to have a value of 5. Well, we got 2 sig figs. Okay, 5.2 times 10 to the 6. Let's see what the units are. Joules per kilogram, kilograms per meter cubed. That'll be joules per meter cubed. On top. And on the bottom, I've got watts per meter. Let's see. A watt is a joule per second. And so I'd have joules per second meter flipped up top. The watts are going to be gone. I'll have meters second over meters cubed, which is seconds per meter squared. Okay, that's not so bad. And we get to use that several times here. So finally, that'll be the time it takes to freeze this thing. So T equals 1/2 times 5.2 times 10 to the 6th seconds per meter squared times X final 2.50 meters, and we square that. And it's going to be a fair amount of time here, but that's okay. I get 1.63 times 10 to the 7th seconds, because the meters squared are going to go away. And if I multiply that by 1 hour over 3,600 seconds times 1 day over 24 hours, that'd be an Earth day. I'm not even going to try to figure out a Mars day. They're 25 hours or something like that, but okay, wouldn't be all that long, actually. Well, let's say 190 days. So that pool is going to be a solid chunk of ice long before the 17 months are up. So it's only going to take a bit over 6 months to freeze that thing solid. Huh, that's not going to be easy to melt either. Better resort to other. Anyway, there's another one of those examples. And hopefully that'll be enough to get you going on that problem 6 on the homework. Okay, starting chapter 18 today. And the first thing we're going to do in there is just consider a few thought experiments. One of them is to add, we're going to be starting by thinking about gases, and we'll actually sort of develop the ideal gas law as just a thought process, and add extra air to a fixed volume. And we'll keep the temperature constant. Temperature constant. So we've got a fixed volume. We're adding extra air. What happens when you're adding extra air? You're increasing the number of particles in there is what you're doing. And what happens? The air pressure inside that thing goes up. When might that happen? Well, have you ever had a tire that's low on air? You put extra air into it. When it's low on air, it may deform a little bit, but its volume inside doesn't change all that much necessarily, because tires are not all that flexible. Shoot, they've got rubber that's that thick on them. They don't easily expand that much. And if they did expand that much, that you might break the steel on them. But that's what happens. The pressure goes up. So P goes up. Okay. Well, what happens if you, oh, shoot, I can show this at school. I've got a little cylinder thing, and it's got a piston on it. And what I can do is just I'll try to remember to do this tomorrow, and put a little bit of cotton in the bottom of it, just tear a little chunk off a cotton pad, and then push down on this cylinder, and you can actually ignite that by doing that. So what happens is you're decreasing the volume and you see the temperature go up in that case. But that's one thing that can happen anyway. Let's suppose you've got a fixed volume and you increase the temperature. And you're not adding more air. So what happens in that case is the pressure goes up in that case too. So pressure goes up. And so we've already got a couple of things here. We've increased the number of particles and we see the pressure goes up if we have a fixed volume. When we've got a fixed volume and we increase the temperature without adding more air, we see the pressure go up in that case. Well, both of these things tell us that the pressure must depend on the number of particles that you have, and it must also depend on the temperature. So from this, we could say that all other things being equal, the pressure is proportional to, and that's what actually it's supposed to look more like something like that, but it's proportional to the temperature. And we could also say that the pressure is proportional to the number of particles. And I'm just going to use a capital N for the number of particles. Okay, what else? What might we do for monkeying around? Oh, we could play with the volume. Well, here we actually did it where we decreased the volume. We didn't change the number of particles in there. Actually, here we did work on it. So that's maybe not quite so easy. But something you could find that if you did it very slowly and could somehow keep the temperature the same, change the volume, like increase volume, keep temp the same, and number of particles the same. So increase volume. Keeping particles the same. And temperature the same. What you'd find in that case, you could have a pressure gauge attached to this thing, is that the pressure actually decreases. And we find out that the pressure is inversely proportional to the volume, all other things being kept the same. You'd get a nice inverse linear relationship, or whatever you want to call that. Well, you combine all these things together and you get something called the ideal gas law. And we're going to write it slightly differently from chemistry, but you can go back and forth between the two actually. And what we get is PV, that may be somewhat familiar, is equal to capital N, and we're going to use a different proportionality constant, and I'm going to put a subscriptive B on it because we've been using K's for a bunch of different things like thermal conductivity and who knows what, spring constants and all sorts of things, but we'd have this equation. Now, this is different from the chemistry version, which looks like PV equals nRT. In the chemistry version, if you've taken that, lowercase n stands for the number of moles of the particles you have. Capital N stands for the number of particles themselves. The R is called the molar gas constant, and it's something like 8.314 joules per mole. I can't remember. It's been a long time. Joules per mole Kelvin is what it is. Well, this K sub B is called Boltzmann's constant, and K sub B is actually equal to, how's it work? Boltzmann's constant is equal to the ideal gas constant divided by Avogadro's number, and the capital N, the number of particles, is equal to the number of moles times Avogadro's number. So we'll just be interested at times in the number of particles we have and so forth. Well, if you divide the ideal gas law or the gas constant, whatever they call it, by N sub A, you end up with K sub B to 3 significant or 4 significant figures is 1.381 times 10 to the minus 23rd. In this case, it's not joules per mole Kelvin, it's just joules per Kelvin. And the minus 23 comes about because you're dividing by Avogadro's number, which that's how that works out. Anyway, let's do some example problems just to see how we might use this thing. And if you haven't taken chemistry, you may never have seen this before, but this thing describes just about everything in there. Now, it's not perfect. Gases are not, this is the ideal gas law, and most gases are not that ideal, although some of them are pretty good. Helium, for instance, will follow this law pretty well all the way down to about 4 Kelvin. And what happens below 4 Kelvin is that the helium turns into a liquid finally. Ordinary air, well before it gets down to 4 Kelvin, you have the nitrogen liquefying and eventually the oxygen liquefying, and I don't remember which order they happen in, but they would be liquids long before they get down to 4 Kelvin anyway. So let's try some problems. And sometimes you don't have to do all that much unit conversion on these things, and I'll show you why. A large cylindrical tank contains 0.750 cubic meters of nitrogen gas at 27.0 degrees Celsius and 1.50 times 10 to the 5th Pascal. Man, I don't remember. We talked a little bit about this, but a Pascal, PA1, and this is definition. It's 1 Newton per square meter. I think we did this back in the speed of sound in air section or something. Anyway, that's what a Pascal happens to be. 1 atmosphere, which you often hear, is about 1.013 times 10 to the 5th, either Pascal or newtons per square meter. They're the same thing. So we have that. Oh, other things. Either version of this, the ideal gas law, either this one or the chemistry one, depend on using the temperature in Kelvin. So we have to be a bit careful with that. Sometimes, if you're talking about a temperature change, you can use either Kelvin or Celsius, but I think we should get in the habit of using Kelvin on these things as quickly as possible. So 27.0 degrees Celsius, that's going to be about 300.1 Kelvin. 0 degrees Celsius is 273.15 Kelvin. So that will help remember. And we're raising the temperature to 157 degrees Celsius. The way I got this was to take 27.0 degrees Celsius and add it to that. And so that wasn't too bad. The 157, I don't trust myself to get that right. So 273 plus 157. And we're only going to be good to the nearest degree Kelvin, actually. So 4.30 times 10 squared Kelvin is that final temperature. Okay, it's got a tight fitting piston, allows the volume to be changed. What will be the pressure if the volume is decreased to 0.480 meters cubed and the temperature is raised to 157 Kelvin? Well, we've got this relation here, PV equals N K sub BT, and oh no, I have to figure out the number of particles, have to do this, have to do that. No, you don't. Look what we can do. We can say P initial, V initial is going to be N K sub B, T initial, and then at the end situation, I've changed the volume. I'm after the final pressure. I can say P final, V final is going to be N K sub B, T final. And I think I'll take this equation and divide it by that equation. So I'll stick the other one underneath it. P initial, V initial, and then N K sub B, T initial. And you can see the N and K sub B are going to divide out. So I don't have to calculate those. So we're just after whatever we're after. P final. So doing a little bit of algebra here, P final will equal. I'm going to wrap things up over here. I'm going to have T final divided by T initial. That's what I had to start with. Over here, I'd have V final over V initial. I'm going to stick those in the bottom because I'm dividing both sides by them, and I'd multiply both sides by P initial. So that's what I have. A little bit of algebra gets me to there. Be careful when you're doing that. And so now I can look at those numbers I've got. P final will equal. Well, T final over T initial is 4.30 times 10 squared Kelvin divided by, I'll call this 3.00 times 10 squared Kelvin. So So that's up there in the numerator. The V final over V initial. Well, let's see. V final is 0.480 meters cubed. And I'm dividing by the V initial, 0.750 meters cubed. And look at the units here. The Kelvin divide out, the meters cubed divide out. So I don't have any horrible unit conversions as I have on some of the earlier thermodynamics problem. And then I have to multiply by the initial pressure, which was 1.50 times 10 to the 5th Pascal. So this ends up not being a bad problem at all. This should work out. Get a pretty good increase in pressure, about 3 point, I think I can keep 3 sig figs on this, 3.36 times 10 to the 5th Pascal. So there, that wasn't too bad. And when you're faced with these problems, if you're going from an initial situation to a final situation, it's best to write them out there in variable form and seeing if just dividing one thing by the other is going to simplify the calculation you have to do. And it definitely did in this case. That's the case with quite a few ideal gas problems. Here's another one, kind of similar. A diver observes a bubble of air rising from the bottom of a lake where the absolute pressure is 3.50 atmospheres to the surface where the pressure is 1.00 atmospheres. The temperature at the bottom is 4 degrees Celsius. That's the temperature at which water is the most dense. And so in a deep lake, which this one is, if you're 3.5 atmospheres down, you're more than 100 feet down anyway. And the temperature at the surface is 23.0 degrees Celsius. That's kind of a nice day. What's the ratio of the volume of the bubble as it reaches the surface to its volume at the bottom? Well, I'm going to set up an equation here. P initial, no, I'm going to use B's. Yeah, this will work. P top, V top equals N K sub B T top. Oh, by the K sub B is Boltzmann's constant. Ludwig Boltzmann was a physicist in the late 1800s, early 1900s, and he was one of the earliest proponents of the atomic model of matter. And at the time, in the late, actually even up until around 1900, not everybody thought the idea, not all scientists thought the idea of atoms was correct. And Boltzmann very much supported it. Albert Einstein showed in a mathematical proof in a 1905 paper that he wrote, pretty sure it was 1905, that random collisions with atoms could produce some effects that had already been observed. And so he kind of helped that model along. Okay, anyway, that's what we've got going at the top. At the bottom, we'd have the pressure at the bottom, the volume at the bottom, is going to equal N K sub B, the temperature at the bottom. And I'm not going to stick any numbers into here till I get this simplified and reorganized the way I like it. As you can probably guess, I'm going to take and divide one of those expressions by the other, and the number of particles and the Boltzmann's constant will divide out. So I don't have to do anything with them yet. And what I get is, let's see, I'm going to regroup things here and have the volume at the top divided by the volume at the bottom divided by the pressure at the bottom divided by the pressure at the top. And make sure you can follow that. And that'll equal the temperature at the top divided by the temperature at the bottom. And the hardest part on this problem is that I have to add 273 degrees Celsius to this number and to that number, which isn't bad. So anyway, the question is, what's the ratio of the volume of the bubble as it reaches the surface to its volume at the bottom? So I really just want VT over VB, because they don't tell me what the volume of the bubble is. So that will equal the pressure at the bottom divided by the pressure at the top times the temperature at the top divided by the temperature at the bottom. So now I can just plug the numbers in here. Pressure at the top is, I think it said 1.00 atmospheres. I don't even have to convert units on that, because as long as the pressure is measured in the same units, they're going to divide out. Whoops, got it backwards. Pressure at the bottom was 3.50 atmospheres. Pressure at the top is 1.00 atmospheres. I can do that division in my head. Temperature at the top, well, 273 plus 4. And you could think of it as 273.15 if you want to. Not that we have enough significant figures to justify worrying about that. Temperature at the bottom. Whoops, I wanted the temperature at the top here. 23.0. Actually, it's a temperature difference now. So 273.15 plus 4.00 Kelvin. So this is going to be bigger than 1. This is going to be bigger than 1. Yep. The volume at the top divided by the volume at the bottom will be six. Pretty sure I didn't mess up, but I get about 3.74. So the bubble's going to be about 3.74 times as big. And the part B of this asks, would it be safe for the diver to hold his breath while ascending from the bottom of the lake to the surface? Why or why not? Well, if you hold your breath, typically you take a lung full of air first, and you'd be filling the little sacs in your lungs with air, which is going to expand to about 3.74 times its volume on the way up. And if you hold your breath, some of those little sacs of stuff, whatever they call them, in your lungs are going to burst, and you'll get blood in your lungs. So that's not a good idea. In fact, scuba divers are trained to exhale while ascending in the water, because otherwise you have things pop, and we don't want that to happen. Okay, couple more of these. Modern vacuum pumps make it easy to attain pressures on the order of 10 to the minus 13 atmospheres in the laboratory. Can't remember when you take a tour of LIGO, which I'm hoping we'll be able to, they talk about the amount of the vacuum that they have in the tubes down there that the laser is shining through, and it's a pretty good vacuum. But anyway, at a pressure of 9 times 10 to the minus 14th atmospheres and an ordinary temperature, say 299 Kelvin, how many molecules are present in a volume of 1.00 centimeters cubed? Well, this is something you can do when you've got this written as PV equals NK sub BT, because this is the actual number of particles. This would be a volume. So if I do a little jumping around here, the number of particles per unit volume is equal to the pressure divided by K sub B times T. Divide that through there. That's the number of particles per unit volume. And it's might be interesting just to do it at 1 atmosphere of pressure and maybe room temperature. So if P equals 1 atmosphere, 1.00 atmospheres, which is 1.00, whoops, it's going to be 1.01 times 10 to the 5th newtons per square meter. That's what 1 atmosphere of pressure is. And the temperature, let's make it 293 Kelvin. Okay, that's pretty close to what we might have in the room. Then the number of particles per unit volume is going to be, this would be in the room, into the 5th newtons per square meter divided by, K sub B, that's the one that I had written over here. It's 1.381 times 10 to the minus 23rd joules per Kelvin. And then I've got the temperature of 293 Kelvin. So we can find out what we've got. Number of particles per unit volume. I think it's going to be a lot. 1.01 times 10 to the 5th divided by those other two things. Okay, unit-wise, a joule, let's see, the kelvins will go away. A joule is a Newton meter. So Newton meter over 1, flip it and multiply, the newtons divide out, and I'll have per meter cubed. And I'll have 2.51 times 10 to the 20th per meter cubed, but it's actually particles per meter cubed. So that's a pretty good number, but it's asking volume of 1.00 times 10 to the 3rd centimeters cubed. Well, if I multiplied that by, let's see, 1 meter over 10 squared centimeters, and then cube that, I'll be dividing this thing by 10 to the 6th. I'll get 2.51 times 10 to the 14th per meter cubed. So, only that many. But a meter cubed, that's about the volume of the tip of your little finger is what that happens to be. So not much. Anyway, let's go back to the problem here and figure that out. The pressure is 9.00 times 10 to the minus 14th atmospheres. And I would multiply that by 1.01 times 10 to the 5th newtons per square meter per 1 atmosphere. And so that pressure ends up in newtons per square meter. Whoa, I missed. Okay, I get 9.09 times 10 to the minus 9th newtons per square meter. Okay, so this really great vacuum, how many particles per, we'll do it in meters first and then do the substitution. 9.09, and I'm using this equation again, times 10 to the minus 9th newtons per square meter, and Boltzmann's constant, 1.381 times 10 to the minus 23rd joules per Kelvin, and then the temperature of 299 Kelvin. Let's see what we get. Okay, I get N over V is going to be 2.2, I have 3 sig figs, 20 times 10 to the 12th per meter cubed, particles per meter cubed, which would just be a placeholder word. But if I multiply by that by 1 meter over 10 squared centimeters, and then cube that, square that, or cube that, and I get 10 to the 6th on the bottom, I'd have 2.20 times 10 to the 6th per centimeter cubed, which is what this one was supposed to be over here. I forgot to put a C on it. And so even at a very low atmospheric pressure, 10 to the minus 13th atmospheres, there are still 2.2 million particles per cubic centimeter. So that seems kind of amazing that you have that many particles in what we'd think of as an essentially perfect vacuum, but it's not so perfect. That's still a lot of particles per cubic centimeter. Okay, relate this to astronomy. I can't do this problem in astronomy class because too much math, but the Lagoon Nebula is a cloud of hydrogen gas about 3,900 light years away. It's a favorite summertime stargazing object through a telescope. It's about 45 light years in diameter, glows because of its high temperature of 7,500 Kelvin. That's warmer than the surface of the sun, by the way, by a couple thousand Kelvin. And the gas is raised to the temperature by the stars that lie within the nebula. It's also very thin, only 80 molecules per cubic centimeter. Okay, that's a lot less than 2.2 million molecules per cubic centimeter. What is the gas pressure in Pascal and then atmospheres in the Lagoon Nebula? And compare that to the laboratory pressure referred to in the previous thing. Okay, and then science fiction films sometimes show starships being buffeted by turbulence as they fly through gas clouds. such as the Lagoon Nebula and science fiction films like Star Trek movies. Yes. However, they're supposedly going faster than the speed of light. So if you can say you can go faster than the speed of light, anything's fair game. Okay. However, the N over V here is going to be 80 per centimeter cubed. And if I multiply that by 10 squared centimeters per meter and cubit, I'd be having 80 times 10 to the 6th per cubic meter, which is 8 times 10 to the 7th per cubic meter. So that's what we have here. Okay, so what's the gas pressure in Pascal in there? Well, PV is equal to N K sub B times T, or the pressure is going to be N over V times K sub B times T. And we know N over V, it's 8 times 10 to the 7th per meter cubed. So we just have to plug in there 8 times 10 to the 7th, and I'll just put 1 over meter cubed for the units on that. Boltzmann's constant, 1.381 times 10 to the 23rd joules per Kelvin. And then multiply that by the temperature here, 7,500 Kelvin. And we'll get something about the pressure here. Boltzmann's constant is a minus 23rd. Okay, it's not much for the pressure. I'm getting basically, we'll just call it 8 times 10 to the minus 12th. Let's see, unit wise, the kelvins go away. This would be joules per meter cubed, but a joule is a Newton meter. So that'll divide with one of those meters, and I'll get newtons per meter squared, which is a Pascal. But it also asks for it in atmospheres. So I'll multiply that by 1 atmosphere, 1.00 atmospheres, although we're not going to have that many significant figures. 1.01 times 10 to the 5th newtons per square meter. And this is going to be a really small number of atmospheres here. Yeah, 8.2 times 10 to the minus 17th atmospheres. And this previous problem talked about a really good atmospheric or heat or vacuum pump in a laboratory, 9 times 10 to the minus 14th atmospheres. This is 1,000th of that value. And this is one of the more dense regions in space, is when you start getting particles like this, or that many particles. So nature beats the best vacuums that we can come up with by quite a bit. So, okay, well, that's an introduction to the ideal gas law as we use it in physics. PV equals NK sub BT, and it's not that different. Several of the problems we solved, we had the N and the K sub B divide out on those things, so we didn't even have to think about their units, but they're not that bad to deal with. So I think, yeah, that was all the problems that I had for today. So we'll stop there. Oh, will we have a review session on the thermodynamics homework? We could. It's not due till midnight tomorrow night, so maybe for 15 minutes or a half hour in the class period tomorrow, we could do that. And see how it works. I'm gonna have a homework assignment over this material that we're looking at this week, but it won't be one that you turn in, but it will be some practice problems for you to work on for this stuff. So you'll get a chance to be working on that before we have a test on thermodynamics next Tuesday. And this is the last week of classes. Next week is finals. So, and we don't have a final, we just have a 4th unit test on thermodynamics. Okay, any other questions that popped up? Things like this are kind of fun, I think, lagoon nebula problems and stuff like that, so. All righty, well, I'll stop recording